Dear students, so far we have seen what is the mechanism by which the Earth's atmosphere has evolved over the period of 4.5 billion years. We started with the primordial atmosphere, which was there at the time of the formation of the Earth. Then we have seen various processes which has resulted in the present day chemical composition of the atmosphere. So today we will continue the discussion to some extent, where we will understand how the atmospheres of the other planets in our solar system are different from the atmosphere of the Earth. Okay, so in the last class we have seen that the evolution of Earth's atmosphere and the evolution of life were hand in hand. I mean, one is totally dependent on the other. Both of them are coupled in a way that one cannot exist, could not have existed without the other. So today we will see major changes in the atmosphere of the other planets in comparison to the Earth. Okay. In our discussion, there was a point where the CO2 levels were taken care by the photosynthesis reaction. That means the CO2 was lost. We have seen that CO2 was a major constituent in the secondary atmosphere, which was basically the volcanic eruptions. Volcanic eruptions have created a lot of CO2. We have seen how much CO2 was there in the system and how this CO2 was lost into the system, into the Earth itself, and right now we do not have much CO2 in the Earth's atmosphere. Okay, so with the decreasing levels of CO2 on the Earth, Earth became more susceptible to ice ages. Let us say CO2 is a very important species because it has the tendency to be excited by the infrared radiation bands. That means that it has the ability to trap the outgoing infrared radiation. The heat is generally given a term as infrared radiation. Infrared radiation is heat. So CO2 has the ability to keep a planet warm. So if you do not have CO2, that means that the planetary surface will be hot when it is exposed to sun, when it is at the daytime, and when you have the night time, the planetary surface will be very cold. That means the average temperatures between the day and night will fluctuate over a very large band. So CO2 is a very important species just because it can hold the heat and it can maintain average temperature, which is not very different from day to night. Okay. So CO2 levels were decreasing due to the photosynthesis reaction, which was happening at a very fast rate, building up a lot of oxygen in the atmosphere, right. So with the lower levels of CO2, with the decreasing levels of CO2, the Earth became more susceptible to ice ages because the temperatures were going down when the solar radiation decreases due to the orbital variations. Okay. Now it appears that nearly 700 to 550 million years ago, the Earth cooled down and became nearly entirely glaciated. So it happened once. I mean, the ice age was there for a reason with the decreasing levels of CO2. Nearly 550 to 750 million years ago, the Earth has cooled enough so that it was nearly an ice age. The entire Earth became nearly glaciated. So it may be possible that how did we got out of this problem? So here it is a very important point to know that when the ice cover on the planet increases, what happens due to the high reflectance of the ice, that means ice has the ability to reflect most of the incoming solar radiation that falls on it. So snow can reflect larger amounts of solar radiation. That means once the ice formed, there is even the solar radiation is reflected more. That means you go into a negative feedback in which the more and more with time, more and more amounts of ice is expected to form, more snow leading to less radiation. So this is a kind of negative feedback which could have resulted. But so this is an artistic impression where the Earth must have turned into a snowball, or let us say a glaciated Earth with the decreasing levels of CO2, which is definitely a possibility. Now, but we didn't completely get an ice ball, or let us say snowball. What happened is there were still volcanic eruptions which were active that time. There were still a lot of volcanic eruptions were still throwing a lot of water vapor and a lot of carbon dioxide into the atmosphere. So, this CO2 was increasing at the same time with the time at the same time as it happened. So, CO2 increased until the greenhouse effect was so large that the earth warmed up and it got out of the ice age. So, once warming has started, it would have happened very rapidly. So, that must have gotten us out of the ice age. Now, in the last 500 million years, so the climate has not been constant with warm periods interrupted by ice ages. So, the average temperature is what I am talking about. So, warm period is some point of time where the average temperatures have gone up, and ice age is the period of time when the average temperatures have gone below the limit. So, much of the variability was forced by changing the solar radiation due to the periodic changes in the Earth's orbital characteristics and tilt. These cycles are called as Milankovitch cycles, and major volcanic eruptions were trying to put as much as CO2 possible into the atmosphere just to make sure the temperature fall beyond a certain limit. Okay. So, there is a chance, I mean there are very little chances of course. So, we can find ice ages in the coming future, and the main reason is that the sun is getting stronger. Now, it is a main sequence star, we know that, right. So, now even the anthropogenic effects such as increasing the levels of CO2 can avoid the formation of or the resulting of snowball Earths. So, this is the average temperature variation over a very long amount of time, a large amount of time. So, what you see is there have been severe warmings and there have been severe coolings. So, now this average temperature is what you see here, and if this average temperature goes beyond a limit, you call this as warming. There are several reasons for this. I mean, this is a very elaborate discussion in itself. So, here what you can see is, so this is what happened, which in its entirety has resulted in the formation of the Earth's atmosphere to the composition that we know today. So, just before we go ahead, we will make a recap. So, the recap is that the Earth's atmosphere was resulted mainly from the volcanic eruptions. Volcanic eruptions gave away a lot of water vapor into the atmosphere. This water vapor was broken or dissociated by the ultraviolet radiation, giving you the initial hints of oxygen, and later a certain other reaction which is called as the photosynthesis reaction took over, and this reaction being fast gave away or created a lot of oxygen in the atmosphere. Right. The nitrogen levels were almost the same since the beginning. Since nitrogen is inert, chemically inert, it won't participate much in the chemical reactions with other species in the atmosphere. So, it remained as it is, and today in today's chemical composition, the Earth's atmosphere is always to be remembered as 78% nitrogen and 21% oxygen. Right. So, this is the chemical composition which we know is very much suitable for the existence of life on this planet. So, this is a very important thing. So, this is what makes the Earth livable or habitable, right. At the beginning we know that the planet Earth has formed by the agglomeration of large sized objects which are called as planetoids. They came together, there was a volatile substance which was trapped in between these rocks, and as the gravity grew stronger, these pieces came together and there was a lot of compression between these pieces, and there was huge temperature increase in this system, and all the heavier elements sank to the deep, or they occupy what is called as the core, and all the lighter elements were raised to the top, right. So, this is what happened. I mean, right. Now, there is a very strong reason for us to believe that since the entire system, the solar system itself resulted out of the nebula of gases and dust. So, every planet that has formed must have formed at the same time as the Earth and must have gone through the same physical or chemical processes which have resulted into the formation of Earth or the Earth's atmosphere. Right. Now, we know it now very well that Earth's atmosphere is the only place which supports the existence of life. Apart from life, Earth's atmosphere is also very different or has a very clear contrast with respect to the atmospheres of the other planets. We will see how it is different, right? Now, it may be interesting to find out what were the processes which went different in other planets, so that now you have a different chemical composition on those planets, right? But that's a discussion in itself, right? So today what we will do is we will not go into the details as such, how or why this composition has resulted on these planets, but rather what we will do is we will see what are the salient features of atmospheres of other planets in our solar system. Okay, now to begin with, let's say the planets in our solar system are mainly categorized into two different types. One, terrestrial planets, and another, jovial planets. Jovian planets are the ones which have no rocky surface, which are basically gas giants, and terrestrial planets are the ones which have rocky surfaces. Let's say that means a surface where you can put your feet on, or a surface where you can land. Okay, so terrestrial planets are the ones which have rocky surfaces, and Jovian planets are the ones which doesn't have a rocky surface. Okay. So terrestrial planets generally have some small amounts of ice, of course, and Earth is the only planet with liquid water as of now that we know today. There are other planets or there are other moons where water is has proven to be present, but that's a discussion away, right? And Jovian planets are mainly characterized by large amounts of ammonia and methane ice with rocky or metallic core. Generally, the first four planets, Mercury, Venus, Earth, and Mars, are terrestrial, and the rest are Jovian. Now, these planets, let's say for example, some of them have not rocky surfaces, but they have ice sheets. I mean, they are frozen, so the entire planet itself is an ice of not liquid or not water, rather it's an ice of gas. Okay, that's a different thing, right? Now let's see one by one. Okay, now let's start with Mercury. Mercury practically has no atmosphere. Only it has only a thin exosphere, which is mainly created by solar wind and micrometeors. Okay, now there were some reports which predicted the formation or existence of ice at the poles, not confirmed anyway. The important feature about Mercury is that Mercury's average temperature fluctuates a lot because of the lack of atmosphere. That's why. So we have already seen, because if you don't have an atmosphere or if you don't have CO2, then your the planet will lose heat easily and will gain heat easily. That means that's why the temperatures on Mercury vary a lot. So Mercury is the closest planet to Earth. Closest planet to the Sun. Of course, it receives immense amount of energy in terms of radiation or particle flux from the Sun. So Sun basically cooks up the entire planet when it is the day, and when it is the night, since there is no source of energy, so the Mercury immediately loses the heat, and the nighttime temperatures reach a very low value of nearly minus 350 Fahrenheit. Okay. Now, then you have the Venus. Venus is to our neighbor, so which has 96% of CO2. So this is a mainly CO2 dominated atmosphere. I mean, it's mainly nothing else actually. So Venus also has sulfuric acid clouds. So Venus has very important phenomena which are not totally understood. It has sulfuric acid clouds suspended in the atmosphere. Its surface temperature goes nearly as high as 900 in Fahrenheit, and it has a very high surface pressure. So this is an interesting phenomena which happens in the Venus. Venus surface pressure is immensely high, which is nearly 90 times more than that of the Earth. Okay, so which is a very big number in itself. Okay. Now, why is it that Venus surface temperatures are very high? Is mainly because of the large amounts of CO2. CO2, we have seen that CO2 tends to trap heat, and it won't allow heat to be given away from the planet, right? We have seen that. So this is basically an example of greenhouse effect, where you see the figure on your left is the Earth, and this is Venus. So what you see, due to the enhanced availability of CO2 to a very large extent, the greenhouse effect is enhanced. I mean, it's an enhanced greenhouse effect which basically traps the outgoing radiation, and it won't allow the outgoing radiation to escape into the space, and it will heat the planet to a very large temperature. So, the point is the Venus is not at a particular distance where the surface temperature is 900, where its surface temperature should be 900 Kelvin, but it is. It is because of the large availability of carbon dioxide, which has the ability to trap the heat. This is just a figure which shows Venus beneath the clouds from the radar measurements. So, you see several patterns on this planet. Right. Then you have the Earth. Of course, we know the chemical composition of Earth and how it has evolved, how it has come to existence today the way it is. We know several other features about the Earth's atmosphere itself, right. Then you have on the right, the nearest neighbor is Mars, which has the surface pressure of Mars is nearly 6 hectopascal, and the atmosphere is 95% is CO2 and small amounts of water vapor. And it has also been seen that in the poles, Mars has the ice formation, ice crystals made up of carbon dioxide and water vapor. And Mars, of course, has a lot of dust. I mean, it has a rocky surface. The average temperature is minus 80 Fahrenheit, but it is generally warmer near the equator in the summers. So, that means the temperature at the poles at the equator is not as low as minus 80 degree Fahrenheit. And it is believed that their water bodies must have existed on the surface of Mars nearly 5 million years ago. So, this is still unverified. Okay, so what a very important, a very prominent feature that you see on the Mars, if you open any image of Mars, you will always be able to see that there are a lot of patterns in which indicate that water must have flowed, or there was water flow on the surface of the planet several million years ago. So, this is how it looks like. The Martian surface looks like the red planet, right. So, and the Martian clouds have also been seen by several spacecrafts, right. Now, when you compare the Martian surface or atmosphere, what generally happens is when a rocky planet's core cools, I mean, now we know that the Earth's core, the molten iron core that we have, the center of the planet is a very hot, it is molten. So, it indicates it is very hot, it is rotating, right. Now, when this core loses its heat, the core can lose heat due to a lot of reasons, due to many reasons. What immediately happens is if the core loses heat, the magnetic field that it generates is mainly lost. So, you lose the dynamo, right, and the tectonic activity which moves the surface in and out. Basically, the Earth's surface actually turns around, we know that. I mean, it happens over several millions of years. It takes several millions of years, but Earth's surface eventually turns out. So, the tectonic activity ceases to exist, and then you have the atmosphere is lost. That is what must have happened to these planets, right. And then you have Jupiter. Jupiter is the gas giant. I mean, that means there is no surface, there is no solid surface to land or to stand, let us say, and which is a Jovian planet by our definition, right. And it is also called as a gas giant. Jupiter is a very large planet. So, atmosphere of Jupiter is mainly 90% hydrogen, and the remaining is helium, methane and ammonia. So, these are present in a very large numbers. So, this also has a very high surface pressure. It has strong magnetic field. The Jupiter has a very strong magnetic field, which is nearly 100 times the Earth. You know, in our discussions in the entire course, two things really matter to us. What are they? One, we will be interested to understand processes about atmosphere. When we say atmosphere, we generally are referring to the processes which are mainly dealing with neutral constituents. Then you have another set of processes which are different, which we generally call as ionosphere, right. So, in the second topic, we will mainly discuss about the plasma processes. So, these are the processes in which you talk about magnetic fields, you talk about charges, you talk about electrons, you talk about plasma, right? So for those discussions, probably the strength of magnetic field or the origin of magnetic field or the shape of magnetic field, these things will be relevant. Okay. So then the next planet is Saturn. Saturn is mainly 75% hydrogen and 25% helium. So Saturn is also hydrogen and helium. This composition is not so different from the composition of Sun itself. We already seen that. So that Sun is also a similar chemical composition. But the only difference is that Sun has as a reactor which fuses hydrogen to form helium, right? The other planets don't have it. This planet is believed to have a rocky metallic interior core. It's the core, not the surface that I'm talking about. And the rings that you see, which nearly span over nearly 18,000 kilometers, are basically held to the planet, to Saturn, by its gravity. And you have another two gas giants, which are Uranus and Neptune. Both of these are gas giants. Let's say Uranus, let's say, which appears in blue-green color, bluish-green color, is due to the crystals of methane that exist on the planet, and the atmosphere is mainly hydrogen and helium again. So, and interior is composed of methane and ammonia and water. So we don't know what exists inside the ice, or icy surface, and the core is composed of rock and metal. These two are the rotational characteristics of the planet. That means it takes a very large amount of time to rotate around the Earth, and it has a huge tilt of nearly 98 degrees on its axis. And Neptune, the farthest planet in our solar system, it has a magnetic field is tilted at 50 degrees, and the atmosphere is mainly hydrogen and helium. So it is more or less similar to the remaining Jovian planets. It has a solid rocky core, and it has 11 satellites. Yeah, it has many satellites. So this was something about comparison with the Earth's atmosphere. So one thing is that terrestrial planets' atmosphere, apart from Earth, is mainly dominated with CO2. For example, Venus and Martian atmosphere is mainly dominated by CO2, and the Jovian planet's atmosphere, to a very large extent, is dominated by hydrogen and helium, right? So we can say that the terrestrial planets, among the terrestrial planets, Earth is a unique example where you have the oxygen and water and so many other things, right? So this is the end of module where we have discussed the evolution of Earth's atmosphere, how atmosphere has formed, how is the atmosphere of the Earth different from the other planets. So in the next lecture, we will try to understand the structure of atmosphere of the Earth, how many different layers of atmosphere exist in the according to the temperature, how does the pressure and density vary with respect to height, things like that. Okay, thank you.